Okay, so I'm going to talk about the Open Energy Monitor project. It's a project that it's a project to build open source energy monitoring and tools for both monitoring energy use in buildings and also monitoring energy production from micro renewables and so on. And it's a project that I started in 2009 in my last year of university. It came out of about 4 different things. I was, first thing, really interested in sustainability. How can we use energy more efficiently? How can we get more energy from sustainable sources? And I really wanted to be able to understand and see how much energy I was using in my own home, and how that related to how much energy I need to generate and these kind of things. I bought an effigy energy monitor. At the time, the only ones that were available were ones that you could clip it around the electricity coming in, and you could bring that to display, but you couldn't get it onto the web. And I'd just come across Arduino and open source and Ubuntu, and was like amazed about this whole open source movement, and everyone was sharing all these designs, and that was really inspiring. And I thought, I'm going to learn more about this, and got really involved with playing about with the Arduino, and realised that it wouldn't be too hard to get an energy monitor that would be able to get web connectivity and do these things. So that was very much the reason why I was interested in starting the project. I was also on the micro renewable side. I've been doing a project with a society at university called Engineers Without Borders to build a 500 watt wind turbine, and we wanted to monitor the power output from this wind turbine, and so that was another aspect of the project that we wanted to explore. So over the last, I started the Open Energy Monitor website, which is this next slide here. This the website on the left here, to document progress on the project, and it's really evolved in all sorts of ways over the last 2 years. It's been really great to see people pick it up around the world, build energy monitors with it, and also be joined throughout by 3 good friends. Glyn Hudson joined last year, and since then the project has really come ahead leaps and bounds, and Glyn's been developing an open source energy monitoring transmitter, which is the unit that clips around the power feed that comes into the house, and that then is part of a full end-to-end energy monitoring system, where you have the transmitter unit, which transmits to a base station, which is where the Nanode comes in and can work, and then that comes up onto the web to an application we've been developing called E1CMS, and that's been the focus of my work, and I'll talk about that at the end. So yeah, we're based up in Snowdonia, North Wales, and up in the mountains. Our nearest neighbour is about a mile away, and you can see the house there with the small PV panels outside, which gives us a little off-grid desk. Yeah, it's a really nice place, and now Glyn's going to talk a bit more about the Monty-X and about the hardware designs behind the hardware.
Okay, cool. Cheers, Trystan. Like Trystan said, we've been working towards putting together this end-to-end open source energy monitoring system, and the idea for this to be, we can sell this as a kit. It'll be plug and play once people sort of build it up, so it'll take data from the multi-active transmitter unit, transmitted wirelessly to the Nanode with an RF module, which will then post data online either to Patchtube or even CMS, an open source energy visualization tool that we've been developing, and also you can display the data graphically on this LCD display. So there's 3 main parts really to this system. The transmitter unit, which we call the E1TX, this can take inputs from multiple CT sensors, from pulse output utility meters. This could also be gas, water, or flow, anything that's like a pulse output. You can also connect an AC to AC adapter if you want to do like real power measurements that can monitor the voltage, or just use a CT clamps and assume the voltage like all of the energy monitors do. There's also an input to take to connect like a one-wire temperature sensor network, so you could have like quite a few one-wire temperature sensors on a one-line bus around the house, monitoring the temperature in different rooms. We're also doing a project to monitor an air source heat pump using these digital sensors. And the third unit is a graphical LCD display. We're just starting to work on this. We're getting quite excited about it. And this will pull data back from the Nanode. So as well as being real-time energy data, it could also be anything else you might want to, any of the data you might want to pull from the web. We'll link that with the energy data. So we're getting quite excited about that. So let's have a look a bit more about depth of the E1TX. So it's a small wireless open source energy monitoring unit. This is what's sort of under the hood. It's more of a PCB design. It's based on the Arduino, and we took the Genome design. I'm sure many of you are familiar with this. It's an open source hardware project. It's an open sourse hardware project based in the Netherlands, and this guy took the Arduino board and he sort of rejiggled it a bit to make it much easier to connect sensors. Because the Arduino footprint is not very convenient to connecting sensors. You've got all digital ports at one end, analog ports, and all powers over there. So he reconfigured those ports to make what he calls a G port, which you got one, you can see on the top right of there, like one interrupt input, analog input output, power, digital input output. And so you have like 4 of these, so it's really easy to plug in like sensor modules. So this is why I based the E1TX design on. You can see those 4 ports haven't soldered in the headers into this board. And around that we've added our energy monitoring circuitry and the wireless module. I'll talk a bit more about the wireless module in a minute. So like the Genome, it runs at 3.3 volts the board. It's because the electrical transmitter unit runs out. And like the Nanode, it needs an FTDI cable to program it to keep costs down. No USB chip on board. USB is just for powering the device. And this is all designed to fit. It's designed to fit nicely in this case. It's one of these sitting through in the kitchen there, monitoring the power of the building. It's going to go and have a look later on. And it's designed sort of run for 2 AA batteries and lasts for about 4 months or so, up to 2 AA batteries. You can have quite a few of these connected to one Nanode base station. We've got a simple demo here. It's possible to have quite a few of these all posting values, whether it's monitoring renewable generation, electricity consumption, or like heat pump temperature monitoring. This is an example of the type of shields that you can plug into it. These are made by a guy, this guy June called Whippler within the Netherlands, who runs the GDAP project, and he churns these boards out on a daily basis. So there's a lot of potential here to do some pretty cool control applications, infrared, relay boards, real-time clocks, like all sorts of things. So the code for the E1TX is all up on GitHub, on the Open Energy Monitor repository there. There's just a couple of examples at present where we hope to flesh this out to have examples for like all sorts of applications for it. So this couple of slides just going to go into the technical details about the RF module. I know a few people have been interested in it. So it's quite a low-cost transceiver module, which means it can transmit and receive. You can buy it from as low as £4 in the UK. It's made by Hope RF, but it's often rebranded by different manufacturers in the UK. They quote 300 meters transmission, but that's obviously in lab conditions. But it's generally enough to go through kind of as many walls as you need it to in the house to get from kind of where your utility meter is to the router. The main problem is when we came to design this, the E1TX, even though in the utility meter cover there's lots of power going around, there's often not a power socket and definitely not an Ethernet socket next to the utility meter. So you need some way to get this data from the cupboard under the stairs to wherever your router is. So this is why we looked at this wireless solution.
Go to my third floor, basically.
Yeah.
This work.
Yeah. It's good news. So you can potentially have quite a few of these connected to one network. You have 28 different nodes and 250 different networks all in the same vicinity. Although I imagine if you get anywhere near those limits, there'll be quite a few problems with collisions. And it's sold in 3 different frequencies over the world. In the UK, we have the 434. We can also use the 868. But since the 434 works all over the world, that's kind of the frequency we're trying to standardise at. It's a surface mount module, but it's not ridiculous. It's quite good for surface mount. It's not, you don't have to be a soldering sort of Jedi to solder it. It's quite easy to solder. It communicates with the Atomic FFT with an SPI interface, and there's a really good interrupt-based library written for it by this guy from G-Labs, and that actually makes it really easy to use. Just as a quick example, getting quite involved now with the C code, but this is just an example to show how simple it is to transmit data. You just set up the module, give it a node ID, give it a network, tell what frequency you want it to work at, define what structure you want to send. Here we're just going to send 2 integers, C21 supply voltage, and you can see at the bottom it's just 2 or 3 lines. That's all you need to send the data in the most simple sort of way. It's the same on the receiver side. Just a couple of lines to receive the data and print it out. So now we've got the eMultiX transmitting end data. We need some way to receive the data on the Nanode. And the good news is the Nanode has been designed for wireless inline. There's a wireless port on the Nanode on the top left-hand side where it says wireless. And this has been designed so that the little breakout board, you can see that on the right from G-Labs, slots straight into it. You don't even need to solder in the frequency voltage regulator or the capacitors to get that power from the board. So that's the good news. The bad news is there's a slight error on the Nanode 5 board layout, meaning the interrupt line from the radio, RFM radio, and the Ethernet connected together, so they all operate at the same time. But it's not difficult to fix this. You just don't solder in R10 resistor, you can see there, and pull out one leg of the Ethernet chip. This connects the 2 lines and allows them to run together. So it's not too difficult to do. It will need to be fixed in Nanode 6. So there we are, that's our end-to-end system we're working on. The last part of this system is this graphical display. And we spent quite a lot of time searching for an open source wireless display that we could use to display energy data as well as anything else. We couldn't really find one, so we thought, well, we'll design our own. And again, building on G-Lab's hardware, he's got this quite nice little 64 by 128 graphical LCD. We've got an early printer pipe we're running on Arduino there. So it's quite a nice little board, quite low power. But the G-Lab's implementation of it is quite clunky. It requires like 3 separate boards, and there's no really easy way to mount it or power it for that matter. So I've been redesigning that board recently. So to make it easier to mount and have everything on one board, so you just have the LCD module and solder straight on. You can easily mount it in like a laser cut plywood fascia and make quite a nice sort of coffee table, internet connected display. So that's the PCB design. It's being manufactured at the moment. Hopefully in the next few weeks we'll have some prototypes working. There's a few things I've added to the board. I've added the temperature sensor module, so you can post the temperature of the living room. That's very relevant when you're monitoring the amount of energy you're using. There's a couple of tricolor LEDs there, so you could make the module glow either red, orange, or green, depending on how much energy you're using. The little a button to switch between modes and a USB port to power it from like a sort of USB power adapter you might have lying around. So we're getting quite excited about this. We'll hopefully build through some pretty cool things like pull in, grid demand, renewable mixed data, and augment that with the energy data from your house. So you'll be able to see what percentage of renewables are in the grid at any given time, and make informed decisions about when you might like to use power. And yes, there's also an idea to pull patching feeds back from the internet to display on the screen. You can display everything you want on it really. Hopefully create some sort of web interface, you know, with the VCI kind of thing, where you can drag boxes around and build your own screen and just send it via an Nanode. It'll appear in your coffee table. So that's the end of the sort of hardware side. Tristan's going to talk a bit about Emon CMS, which is an energy visualization web application which we've been developing. We've got quite a few Emon X's with us. We've got quite a few kits which we can sell if you'd like to build your own one. We've also got quite a few pre-built ones lying around to have a look at. We've got a prototype running of the screen, and there's also a live feed from this building being transmitted from the kitchen there to a Nanode but connected to a router. And Trystan will show you that being posted live on my web at the moment. So you can have a look at that later on.
So I'm going to talk about the next step of the system is how the Nanode relays the information up to the web. There's a load of code on GitHub here, a lot of examples for both DHCP, DNS, for both Apache and for Emon CMS, which I'll talk about now. So yeah, have a look at those if you're trying to get your Nanodes to connect. Right, so Emon CMS is an open source web application for processing, logging, and visualizing energy, temperature, and other environmental data. And it really came out of, I was doing some work for the Centre for Alternative Technology, and we needed to be able to, they got a lot of different renewables on site and and obviously lots of loads. And we wanted to create some public displays to display and show how energy is generated and used on site. And the internet connection isn't always very reliable, so we needed to have something that would run on local servers and be able to serve data as fast as possible to these displays. So the website, the web application is programmed in PHP, stores data in a MySQL database, runs on a LAMP server, and it uses JavaScript and the Flot JavaScript jQuery plugin to do the graphing, which I'll show you now. So there are a couple of aims for the use of Emon CMS. One is for our own use for doing energy dashboards for home connected energy monitors, and doing heat pump logging, also hot water. You can really do some quite complex visualization. So I'll just break out of this now and go to a live example. So this is the login screen. I'll just create a user. So the first thing you see is you've got an API key in order to authenticate access to Emon CMS. You've got both a write only, so this is one that you put on the Nanode to tell it to when you want to send data to Emon CMS, and the other one is you'd embed it in your visualization. Say you want to embed a visualization on another web page, that will allow access to the data on Emon CMS for that visualization. This URL example here is what you'd copy and put on a Nanode. I'll just copy it and run it through the web browser so you can see this working. So it returns an OK, so to say it got to the server. And then we can see that it appears in inputs. And one of the, as well as needing to be like a web application that you could run on a local server, it's also designed specifically with energy data in mind. And there's a feature that done a lot of work on is input processing, which is being able to take, not just logging feeds as they come in, but being able to take feeds as inputs and then do processing on those inputs in order to say you want to calibrate a temperature value, or the one that's really useful for energy monitoring is converting instantaneous power data into kilowatt hour per day data, which is like bar graphs of how much electricity you use per day. This slide here shows how on the left you've got the inputs, and you can take it through these sort of processing boxes to get your different outputs and then store them as different feeds. So an interesting thing you can do is you can take a voltage and a current feed from and then multiply them on your CMS into a power feed, and then you can convert that to kilowatt hours per day and do all the different processing steps. So the processing works by, you click on this button here. Should work. And then you can select from this drop-down menu a series of different processes. So the log to feed is the basic one. Power to kilowatt hours a day converts it into data that you can generate these bar stacks in an efficient way. So I'll log out just to show an actual a demo of one with more data in it. So this is a feed from Glyn's house, and there's also a feed from this room. I'll show you this one first because we can show like the long-term data feed. The idea is you can zoom in and out from really large different resolutions on data. So you can go into like, it posts up to this at once every 10-second interval. So you've got, to start with, you've got really high resolution on your measurements. And then you can, but at the same time, you can zoom out to get a note you can zoom right out to see long term. It's not so useful with instantaneous data, it just looks like a load of bits of mess really. So you wouldn't really do this with power data, but it's more useful with temperature data where you can see a trend. And then kilowatt hour. So this is sort of an example of a bar graph, how much electricity you use day to day. You can zoom out to a year, and zoom in on different parts.
So to do these bar graphs, did you have to do this calculation?
Yeah.
You had to do that. You had to convert it to kilowatt hours per day in order to bar graph.
That's it. Yeah. So there was the power feed coming in that was logged to create that instantaneous graph. But it was also converted into kilowatt hour per day data, which is stored in a second table, and that's just one value per day. And then that allows you to generate that graph much faster than if you had to do the processing as a second step.
Can you make new things. For example, outside temperature minus inside temperature. If you add a little thing like this, for example, have you ever done the calculation?
Not yet. You've got a set list of the calculations, but if you wanted to get involved with the PHP side, there's definitely scope. So, as I said, I've been doing work at the Centre for Alternative Technology, and this is a visualization we created to show electricity generation and load on site. This block here is the energy generated in width of it is the energy used today, and then how it's divided is where that energy's come from. So far we've got 119 kilowatt-hours a day, kilowatt-hours from the grid, and 23 from on-site generation. That's a percentage. Looks a bit. So now you can explore how much it was yesterday, week, and month. So the idea here is to try and create some visualizations that would allow you to at a glance understand what the power, the energy picture is on site. And then you've got a bar graph here which allows you to see throughout the year, September, October, November, what percentage of on-site versus off-site energy was getting. So you can click on July. You can see here, probably some weeks you'd have a lot of sun, and so you'd see that the on-site generation is really going up a lot, because they've got some big PV arrays there. Another useful visualization for energy data is being able to see how much each day costs. And then being able to compare, say, 2 different days to say, well, if I used electricity on that day, the same amount of electricity every day, it would cost £412. But if I did whatever measure allowed me to have use that much electricity a day, I'd be saving. I was at about 30 quid in that year, or more. You can see it. It sort of helps. Hopefully, this kind of information would help you understand or see where savings can be made. And then you can do some cool things like zooming in on the data and going right in and seeing how much breakfast costs and so on. This one I quite like is being able to combine, say, temperature data with energy data and being able to see how temperature affects heat input to a building. So I'll just so what we have here is the red one is outside temperature, the blue one is temperature in the living room, and the heaters is storage heater, electric storage heater input. So if I zoom out for 2 months and then go a bit further out, you can really see the way that as temperature increases, the heat input, heat demand for the building really goes down for maintaining that same level of comfort in the house. Yeah, I should have that one. So all the code for this is up on GitHub. And I'd love to have anyone's input on the code. I think there are ways to improve it, other features that would be good to do. That would be really fantastic to have. some feedback on it. It's based on a model view controller architecture. You've got the database, which is the models in the database create these PHP functions which you can use in the other part of your code, and it's a bit like, say, an Arduino library where you can include these functions and allow you to do a lot of things that make the program work, so create feed, insert feed data, and so on. The idea with model view controller is that you can make it really modular and you can change blocks and reuse code. And one thing I'm interested in doing is swapping out the database for PatchPay, and because you could use PatchPay as the data store, and that could be quite a useful feature for people who are putting lots of feeds onto PatchPay.
So can I ask you, I'm a little bit confused between the interaction between like the Untitled CMC and HatchPay and like things speak or things talk or whatever. Like, why one of the things I like about your system is you can install it on your server, right?
Yeah.
So why would you want to kind of go towards HatchPay as the place where you put the data? Or what's the benefit of these different ways of doing things?
Yeah, well, I like the idea of having that all those options are available, so depending on what your needs are. You might want to use PatchPay as the back end if you didn't have access to your own servers and you weren't interested in maintaining your own installation or server, and therefore like PatchPay could handle that for you. So it's just having those options really.
So if you use PatchPay as the server side stuff, where would you install the front end?
That would, it might be that we need to host a version of V1CMS that was, there would need to be a version of V1CMS on another server that then mirrored through to PatchPay. That maybe could be something that if people were interested, we could pull resources together and do that.
But at the moment, I can sign up for an account on your system. So it's a little bit like PatchPay in the moment. So like in the moment, I can send data to you guys and install it on your server, or I have to install it on my.
Yeah, you have to install it on your server. We're not offering a service at the moment. But at the same time, if people are interested, and especially interested in it at the same time, at looking at the code itself and improving it, because it's not at that stage where it's probably ready to do like a service type of deployment. So it would be, but if people were interested, we could pull resources, get a dedicated server, and maybe have like 100 feeds going up or something. Using this looking to. So just to finish, I'll show you, as I said, we've got the energy monitor in the cupboard here, and that's posted into this. We've got this little screen here which shows the power of the building. Does that come through? If you want to pass it around.
I'll go put the kettle on.
Yeah.
Something's awesome.
So you use one battery for the whole unit?
Yeah, that's just like a prototype. That's 14 hours hardware.
And it's internally upgraded to 3.2?
Yeah, there's a booster converter in there.
So this is a real-time power feed from the building here.
You see what
I think that's it
this morning?
Yeah, I think we only connected it like an hour or so ago.
So, do you mind me asking, so what can you tell from this section? Like, what's going on here? Like, there's obviously the spikes, but it's almost like the general level has gone up a slight.
Okay, the coffee machine is on, and that could add, what's the scale, that could quite easily come on and add 100 watts or so.
Probably, if it's keeping the hot water boilers on, so it could be on a thermostat going on and on off.
That's probably the spikes.
That's what the spikes are, yeah.
Or a fridge going on is about 50 watts. So,
I saw another pattern that seemed to have this almost this compressor pattern. Like, what do you do with this stuff? Like, do you look at the spikes or you look at the threshold of this stuff?
Well, the useful thing is, say you've got feed, it's easier to do with the feed from the house.
I got my house around 80 watts.
So this is say over a couple of days, and you can see the fridge going on and off, and you'll be able to look at how much energy that fridge. If you wanted to, you can really zoom in and look at it. And say, okay, the fridge is using this amount, and would a better fridge save energy? Or you can look at the baseline. What point in the day does it go to the lowest point? Because you might not be watching the screen all day, so this is a way of just coming to it at one point and then finding out all this information. Things that are really useful is we have an immersion heater to heat our water, and it's just with only an on-off switch and a thermostat. But when you put the switch on, you don't really know how long it's going to take or we didn't know how long it was going to take to heat up the water. And it was possible to look at that graph and see that sometimes we were leaving it on for an hour too long. It was just going on and off, wasting more and more power. And so we got an idea, right, it heats it up in 40 minutes, and that allowed us to save about 2 kilowatt hours a day, which was about the amount that you produce from a 2 kilowatt PV array. So you know, if you can make these savings through just making more effective use of your energy, then you have less demand on the renewables that you might install, and they'll cover a larger percentage of your household use. So that's the aim of all this, really. Yeah, that's it. Thank you very much.
Thanks very much.